In this tutorial, I'm going to cover two questions. Question 9, that is based on electricity and magnetism, electrodynamics, that is DBE 2022, and also the optical phenomena, also known as the photoelectric effect, which is question 10. So I'm going to cover them both in this tutorial. Now let's get into question 9. It says here that the simplified sketch of an electric motor is shown below. So we are given the sketch over here. Write down the energy conversion that takes place in this motor. So this is an electric motor. We are answering 9.1.1. We know that an electric motor converts electrical energy to mechanical energy. Okay, that's why over here we have got a power supply, a battery. So this will supply the electricity, which is electrical energy, and then that electricity is going to be turned into rotational energy, which is the mechanical, the movement of the coil. Okay, then the next question is 9.1.2. Is the motor above an AC or a DC motor? 9.1.2. Okay, we identify an AC or DC motor. We identify it by looking at this part here, which is a commutator. In this case, we have got a split ring commutator, which tells us that it is a DC motor. Okay, it is a DC motor. If it was an AC, we would have a slip ring. So in this case, our answer to that question is DC. It is a DC motor. Okay, 9.1.3. What is the function of the commutator in this motor? So what is the function of the split ring commutator? Now the function of the commutator is to ensure that the coil will always rotate in one direction. So we can say that it ensures continuous rotation of the coil. Continuous rotation of the coil, so that the coil will always rotate in one direction. Or you can also give your answer as it ensures that there's a change in current. Ensures a change in the direction of the current. Direction of current in the coil. So then 9.2 is the next question. A resistor Y is rated 220 volt, 100 watt, and is connected to a 220 AC source as shown in the circuit below. So we are given the circuit over here, and then we are required to calculate the resistance of resistor Y. So here we are given two variables, which is potential difference and power. So we are going to use the power equation to calculate the formula to calculate the resistor for Y. Now we know that we have got the three equations for power. We can have number 1, P average is equal to V squared RMS over R. Okay, that is the first one. The second one is P average is equal to I squared RMS, okay, times R, times the resistance. And the number 3, we have got the P average is equal to V RMS times I RMS. Okay, so these are the three equations. So from the variables given here, we can see that we are given V RMS Okay, and we are given power, which is W, and now we are calculating R. So we can use the first equation here, which is P, V, and R. So let's use equation 1 to calculate the power. So what is our P? Our P is 100 is equal to V squared, which is 220 squared over R. Okay, this translates to our R is equal to 220 squared over 100. We can enter that into the calculator, which is 220 squared divided by 100. Okay, that is 484. So our resistance for Y is 484 ohms. Now we are given another resistor Z with a rating 220 V, and the X watt, which is unknown power, is now connected in series to resistor Y and to the same source AC. See the diagram below. The power dissipated by resistor Y changes to 80 watts, while its resistance remains constant. Calculate the power rating of resistor Z, assuming that resistor Z has constant resistance. So we want to calculate the rating of resistor Z. What is the power for Z? Now, going back to the three formulae that we have stated earlier, these ones. So to calculate the power of a component or a resistor, one, we need the V. In this case, we know the V for Z, which is 220, okay, because that is the rating. For that, we know our V, but now we need to find the resistor, okay? Or we can use the current. We need to find the current in Z. Then once we know the current in Z, then we can calculate the resistance for R, okay? Or if we know the V and then we know the I, the current here, then we can also calculate. So you will find that out of all these options, okay, let's choose, we are going to choose equation 1, but there's an option to use any one of them. So we are going to choose equation 1. Okay, so for us to find equation 1, we need to calculate the resistance of Z, the resistance of Z. Okay, because the V we know is 220, the rating there it says 220, but now we need to know the R. Okay, so let's take that. Now to calculate the resistance of Z rather, we have to work with the Y first. So we are given that the power at Y is 8 watt. So here we have got 8 watt here. Okay, the wattage here is 8, and we know the resistance for this one is still the same, which is our resistance is 484. So let's calculate the I'm going to calculate the V here. Okay, what is the potential difference at Y? Now, if I know the potential difference at Y, I'll know the potential difference at Z. Okay, now the potential difference of Z will give me the resistance at Z. So now let's do it that way. Then we have got, so let's calculate the power here. The V here. So we can say, okay, for resistor, this is 9.2.2. I will start by calculating the IRMS. What is the IRMS? Okay, at what is how much current is coming here? Okay, we know that the IRMS, we can use the formula using the power. IRMS, let me just start from there. Delete this one. Okay, we can use the power that is given for Z. Now let me say for resistor Y. Let's put it that way. So for resistor Y, we've got the P average is equal to, because I want current, I'm going to use the formula for current, which is I RMS squared, okay, times the resistance for that. Okay, our P average we are given is 80 is equal to the current is what we want, I RMS times 484. The resistance for Y is still the same. Okay, so now let's calculate that one. That will give us our I will be equal to the square root of, because when we divide there, it's going to give us the square root of 80 over 484. Okay, let's punch that in our calculator. So we have got the root of 80 over 484 is equal to, change that one, 0.4065. So I'll give it as 0.407 amps. Now that is the current at Y. Now I'm going to calculate the V at Y. What is the V at Y? So the V RMS at Y, what is the potential difference here? The potential difference is I RMS times R. Okay, the current that is coming in here, which is what we have calculated, times the resistance for that one, which is going to give us 0.407 multiplied by 484. Okay, how much does that give us? Okay, I have got this one 0.407 multiplied by 484. I'm getting 196.988 to 196.988. Now, why are we calculating this one? Let's come to, because now we want to calculate the resistance for Z. So let's go for resistor Z. For resistor Z here, what we have now for resistor Z, we know that the potential difference here is 220. So we know that if we take 220, this will be equal to V for Y, potential difference for Y, plus the potential difference for Z. Okay, now what is the potential difference for Z? So now to get the potential difference for Z, which is Vz, you see here we are going to take the 220, subtract the V for Y, the potential difference for Y. That's why we calculated that 196, that is 196.988. Okay, let's subtract that one. I've got this one, so I'm going to subtract 220. We know it will be negative, but we'll just we ignore the sign there. That will be 23.012. Okay, so our V is going to be 23.102. Is it 012? That is 23.012. Yes, 012. So we need to make a correction here. That is 012. Okay, so that is the V at Z. Now we've gotten the V for Z. Now we know there's the current that is coming in here. The current in Y is the same as the current in Z. So we will want to calculate the resistance at Z. So what is the resistance? We can use V is equal to IR. Okay, we can say VRMS is equal to IRMS times R. Okay. And from here we know our IRMS is going to be the VRMS, which is this one that we have gotten here, 23.012 over the R, which is R here. Now the IRMS, we know the current that is there is 0.47 because it's still the same one. So it's going to be 0.407 is equal to 23.012 over R, okay, which gives us, let's take it here and say our R is going to be 23.012 divided by 0.407. How much do we get from there? Okay, I'll just take this number, it's still a negative. I will just divide it by 0.407. We are getting how much here? 56.54. So this is 56.54 ohms. So now we got the R, which is the main variable that we need now. So we need to find now the power for X. So we can pick any formula here. We have got the liberty now. I think this one is the most suitable. We know the V is 220, it's given. We just have to divide by R. Okay. And in this case, we're gonna say therefore the rating at X, which is the P average, it will give us how much? V squared over VRMS over the R. And this is going to give us the VRMS is 220 squared over 56.54. Okay, let's go on to divide that one. 220 squared over 56.54. We are getting here 856.03. So 856.03 watt. So that will be the power for X. Okay. Let's get into optical phenomena and properties of materials, which is the photoelectric equation, the photoelectric effect. The second question we are going to handle in this tutorial. Question 10. The apparatus illustrated in the simplified diagram below is used to demonstrate the photoelectric effect. So we are familiar with this diagram here. So there is incident light. Okay. There's incident light, incident on the metal, shining there on the metal, and then electrons are emitted from the surface of the metal. So define the term photoelectric effect. It's one of the common questions that we always meet under this topic. So what is a photoelectric effect? We can write it as the photoelectric effect is, let's start by saying it is a phenomenon, or you can say a process / process. Okay, where electrons are emitted, let's say, or ejected from the surface of a metal, when light of a suitable frequency is incident, means when it is shining on the metal, is incident on the metal. So it is a phenomenon or process where electrons are ejected from the surface of a metal when light of a suitable frequency, or you can put it as when electromagnetic radiation of a suitable frequency is incident on the metal. That is a 10.1.1. And then coming to the question, incident light of frequency, we are given the frequency over here, which is 1.2 times 10 to the power 15 hertz, is shown onto the metal plate, and electrons are emitted. So this incident light here, frequency here is 1.2 times 10 to the power 15 hertz. So calculate the number of photoelectrons emitted in 1 second if the total energy transferred by the light to the metal per second is 1,75. So basically here we are given that the total energy that we have is 1,75. So how many electrons, do we need to constitute that amount of energy? So we know that for every incident light, the particle nature of light says that the light is made up of particles, and each particle is a photon. So that photon has got energy, and we can calculate the energy of each photon. That is 10.12 energy of each photon using the formula H is equal to E is equal to HF, where E is the energy of the photon, H is the Planck's constant, and F. So we need now to calculate what is the energy of each electron, so each photon. So the energy of each photon when the frequency is 1.2 is 6,63, that is Planck's constant, times 10 to the power negative 34 multiplied by the frequency of that particular light, 1,2 times 10 to the power 15. So this is the energy of each electron. Let's enter it into our calculator. So we have 6.63 negative 34 minus 34 multiplied by 1.2 15 there. What do we get? I am getting 7.956 times 10 to the power minus 19. 7.956 times 10 to the power negative 19 joule. So this is the energy of one photon. Now, so how many photons would we need to have this amount of energy, this total amount of energy? So we can say here, therefore, the total number of electrons, therefore, number of electrons that we need is to divide this number, the total energy, divided by the energy of each electron. So that will be 1.75 by 10 to the power, that is negative 9, divided by the energy of each photon, 7.956 times 10 to the power negative 19. So let's punch that one in. So we have here 1.75 negative 9 divided by 7,956 negative 19. And how much do we get there? I'm getting 2.23. That is 2.23 by 10 to the power. What is our power here? It's not given in exponential. Let's set it up to scientific 6 there and see what we get. I'll put 9. How much do I get? Oh no, I set it up to fixed. I want scientific is number 7. 7, 9 there. So that is a 2.23 by 10 to the power 9. That is 10 to the power 9. So that is the number of electrons that we need. Okay, now for 10.13, we are required to calculate the maximum speed of a photoelectron if the threshold frequency, that is a threshold frequency here, threshold frequency is F0 there, of the metal plate is 9.1. Now, what is the maximum kinetic energy? So here we have to use the photoelectric equation. We are given 10.1.3, 10.1.3. E, the energy of a photon, is split into the work function plus the EK max. Okay, and of course we know now the energy of our photon, which is 7.956. So that is 7.956 times 10 to the power negative 19. Okay, this is split into the work function. The work function is, for now, we can put in the formula, is Planck's constant times the threshold frequency, okay, plus the EK max is half mv squared. So m being the mass of the electron, and we are required to find the v. So we know the h, we know the cutoff frequency or the threshold frequency, we know the m, so we can substitute everything here, and then we can calculate our v squared. So we've got a 7.956 by 10 to the power negative 19 is equal to h, which is 6.63 times 10 to the power negative 34. This formula, you'll be given them, they are constants. So you'll be given them as constants in your table. We have got your Planck's constant over here, and you also have the electron mass, which we are going to substitute. So we can use them. You can always refer from your formula sheet. I just know them by head now from memory, so there's no problem with that. And then F cutoff frequency is, we are given 9 point, that is, so we are going to multiply by 9.09, okay, times 10 to the power 14, okay, plus, okay, half mv squared, so plus a half times m, 9.11 times 10 to the power negative 31. Okay, so that is the mass of an electron, 9.11 times 10 to the power negative 1. Okay, and then that one we multiplied by v squared. Okay, so v squared, was we are required to find the and the v. So now what we get here, once you make all these substitutions, you have got the majority of the answers from the 5 marks. I think the only 1 mark left here is to calculate your v. So what are we going to do with this one? We will take the 7.95 and we subtract this one here, then we'll get that, and then we divide. Okay, I guess you follow me here. We can say, what is our v squared? So take this one over, that is 7.956 times 10 to the power negative 19. Okay, I'm going to subtract this, okay, because it's added to the v squared here. So subtract 6.63 times 10 to the power negative 34 times 9.09 times 10 to the power 14. Okay, and all that I will divide by this value here, which is a half into 9.11 times 10 to the power negative 31. Okay, so that will give me a root. Now let me just put in my square root for now. So I'll just rub here, and then I'll put in the square root because it's a V. So let's find the square root of all that. Okay, then punch it into the calculator. So let's get into the calculator here. So what do we have? Let's put the square root sign there, and then we've got the fractions. So we're going to enter numbers on top there, 7.956 and the negative 19. Okay, we are subtracting 6.63 negative 34. Okay, and no, we must multiply here. Okay, I guess we've made a mistake. See, there's a multiplication here. That is a delete there. Must be a multiplication. Yeah, we have multiplied by 10. And then what are we gonna get? Right, and then I'm going to multiply again. Multiply by 9.09, 9.09, and that is multiplied to the power 14. Then I'll come down to 1 over 2 at the bottom, multiplying 9.11, and that is multiplying negative 31. Okay, I'll close here. Let's see if we get some luck. So I'm getting how much? 6,554 times 10 to the power 5. So that will be 6,554 times 10 to the power 5. That is meters per second. So that will give us the velocity of that particular electron, or the photoelectron. Now 10.2, proceeding to 10.2, briefly explain how an emission spectrum is formed in terms of energy transitions. Okay, we know that we have got the two types of spectra. We've got the emission spectrum and we have got the absorption spectrum. So basically, an emission spectrum, that is 10.1. So an emission spectrum is formed, okay, let's say it is formed when an electron or electrons, when an electron returns, or an electron moves from a higher energy state to, or state is a level, to a lower energy state, and thereby releasing energy, and therefore energy is released in the form of light. Okay, in the form of light. So when an electron is moving from a high energy state or a high energy level to a lower energy level, so there is energy that is released in the form of light, and the frequency of that particular light would determine the energy level that the electron will have moved through. Okay, so that is how you can briefly explain the emission spectrum. With the absorption spectrum, who is the opposite, where an electron moves from a lower energy state to a a high energy. In other words, it absorbs energy. In this case, there is release of energy. Okay, that brings us to the end of this section. Thank you for watching.